Okay, I'm looking at the exploration on page 79 in the lab manual, and we've just done Riemann sums, so we have seen that the area under the graph of a function y equals f of x and above the x-axis can be approximated by using a series of calculated areas of rectangular regions. Using more rectangles yields a more accurate approximation. In fact, we found that the exact area could be computed by finding the limit of an infinite number of rectangular regions, and we know that f of x sub I is the height of each rectangle, delta x is the width of each rectangle. And so what we want to do is we want to look at this a different way. So we already have found the area under this curve, f of t equals 2t plus 3. It's right here. Right here. This is f of t equals 2t plus 3, and you've already found the area from 1 to 4, and we're going to do that again using h of t, a equals h over 2 times b1 plus b2. And then we're going to answer these questions. Okay, so first, let's just remind ourselves what the area was from 1 to 4. So remember, from 1 to 4, the height of this trapezoid was 3, and f of 1 gives us the length of base 1, and f of 4 gives us the length of base 2. So if we put it in here, a equals 3 over 2 times 5 plus 11. A equals 3 over 2 times 16. That's the same as 3 times 8, which is 24 units squared. So we know that it's 24. Okay, so now what we're going to do, using the same formula, we're going to calculate the area bounded by the graph f of t, graph of f of t. Let's call that f of t right here. From t equals 1, right here, to x, right here. And we're going to use the same formula right here. So now we have an x, so the way we found this distance 3 was, well, we did 4 minus 1, so this would be x minus 1 is our height, and f of 1 we know is 5, and f of x, or f of x in this function would be 2x plus 3, so that is our height here. So if we plug it into the formula, a equals the height, which is x minus 1, over 2, times b1, which is 5, plus b2, which is 2x plus 3, gives us a equals x over 1 over 2 times 8 plus 2x. Just cancel out this 2 with both of these, and you get a equals x minus 1 times 4 plus x. And so we have a function in terms of x, and if I multiply it out, I'm going to get, let's move this around, so it's x minus 1 times x plus 4. So you can see what we're going to get here is x squared plus 3x minus 4. So now we have a function that's going to calculate any area from 1 to x. So that's number 2. Okay, and then it says your answer from part 2 can be thought of as an area function, a of x, which measures the area under the curve from 1 to x. And it says find a of 4 using this function. Okay, so if we want to find a of 4, we'll plug 4 in. 4 squared is 16, 3 times 4 is 12, minus 4. A of 4 is 28 minus 4. A of 4 is 24 units squared, which is what we had when we had 1 here and 4 there. So this function works. Okay, so then number 4 says use the area function a of x to find a of 1, and what does this represent geometrically? So we know the function works. So I'm just going to use this so we can see. So our function is x squared plus 3x minus 4. So a of 1 equals 1 squared, which is 1, plus 3 times 1 is 3, minus 4, which is 0 units squared. Which makes sense, because if we're here at x equal 1 and we're evaluating a of 1, then the area of that trapezoid is obviously 0. Okay, question 5 says use the area function a of x to find the area from x equals 3 to x equals 6. Well, this function right here, this is f of t equals 2t plus 3. This function right here only is the function that'll give us the area when x is 1 to x. So what we have to do is we have to be clever about it. If we want to find the area from 3 to 6, what we can do is find the area from 1 to 6 using this function. So find a of 6, and then find the area from 1 to 3. And then if we subtract out 1 to 6 area minus 1 to 3 area, we'll get the area from 3 to 6. So let's do that. I want you to be able to see. So a of 6 is 6 squared, which is 36, plus 3 times 6, which is 18, minus 4, which is 54 minus 4, which is 50 units squared. And a of 3 is 3 squared is 9, plus 3 times 3 is 9, minus 4. So a of 3 is 18 minus 4, which is 14 units squared. Okay, so what we have here is that a of 6 is this whole thing. It's 50. A of 3 is this here, which was 14, and so 50 minus 14 gives us 36 units squared, and that's the area from 3 to 6. Alright, we're going to skip number 6, and we're going to look at 7. It says, how can we determine an expression for the rate of change of this function? So this is our function, x squared plus 3x minus 4, and we want to find a rate of change. Well, what is a rate of change? Instantaneous rate of change is the derivative of this, so let's take the derivative of this. The derivative of x squared is 2x, and the derivative of 3x is 3. And then question 8, what is the relationship between the area function and the original function in our graph, which was f of t equals 2t plus 3? And you can see it here. This was the line that we used to calculate the area under the curve. So if we have this function f of t equals 2t plus 3, we have seen that that's the derivative of the function that's going to calculate the area under the curve. So if we go this way, if we call this area function the area and this a prime of x, that's the derivative. Well, if we go this way and call this the function, then this area function is the antiderivative. So what this means is, if a of x is the function that describes the area under the curve of y equals f of x from a to b, we have this relationship that this f of x is the derivative of this. In this case, though, we call a of x the antiderivative of f of x. And furthermore, it turns out the area can be computed by a of b minus a of a. What that means is, if I give you a lower limit like a and an upper limit like b, in a function like 2t plus 3, I can take the antiderivative of this function, evaluate it at b, and then evaluate it at a, and subtract the 2. So the antiderivative of f of x is not a unique function. We skipped a little bit, but it turns out that if we had done this together instead of separate right here, if I had done this together instead of separate, if I had done a of 6 minus a of 3, just watch what happens really quick. A of 6 is 36 plus 18 minus 4 minus 9 plus 9 minus 4. Okay, so 36 minus 9 gives you 29, and 18 minus 9 gives you a positive 9. But what does negative 4 minus a negative 4 give you? 0. So this is a 27, and that's going to give you 36. So see how these cancel? All right, that's the point here, that when you have a lower limit and an upper limit and you are evaluating, then there's a lot of functions. The c part doesn't really matter. So when you don't have an upper limit and a lower limit, that's called the indefinite integral, and you need a plus c. But as soon as I give you a lower limit and an upper limit, you don't need to worry about the plus c anymore, because you're going to find the antiderivative and evaluate it at b, subtract the antiderivative evaluated at a, and any constants will cancel out. Okay, so let's see if we can apply this now with different shapes. So we have this function 4 minus 2x, and we want to find the area under this curve, which is pink here. And so what this would look like if you were going to set up a definite integral, it would be this. It would be the integral evaluated from 0 to 2 of 4 minus 2x dx. So what you would want to do is you want to take the antiderivative, which would be 4x minus 2x squared over 2, and you're going to evaluate it from 0 to 2. And so that means you're going to plug 2 in. So that'd be 4 times 2 minus 2 squared. And then you're going to subtract 4 times 0 minus 0 squared. So that's going to give you 8 minus 4 minus 0, which is going to give you 4 minus 0, or 4 units squared. Alright, now at this point, now that we're finally looking at integrals, I did want to make a connection. Remember when we did Riemann sums? Riemann sums were the limit as n approaches infinity of the sum I equals 1 to n of f of x sub I times delta x. And remember how that height, that f of x, was the height of the rectangle, and that's the function. That's right there. That's the function. And this delta x is the width of the rectangle, and that triangle stands for delta. Well, now it's going to change to a d for delta, dx. And this sum means add up all the rectangles. Well, that looks like an S because it is. It stands for sum. So there's a huge connection between these Riemann sums, rectangles, and this integrating. And this is the exact area. This you had to use a lot of rectangles to make it pretty accurate, because we can't make n go to infinite number of rectangles, but now we can. So this is how you find the area under the curve. This is also how you find the area under the curve. You integrate the function and evaluate its upper limit, evaluate its lower limit, and you subtract. We can check this. We know the formula for a triangle is 1/2 the base, which is 2, times the height, which is 4, and 1/2, 2 times 4 is 4. So this checks out. Okay, let's find the area under this curve, y equals x squared. And so we'll set it up. We want to find the area under the x squared curve, and we're evaluating from 0 up to 2. So what that means is you're going to take the antiderivative, that would be x cubed over 3. And this is a different way to write it. And you're going to evaluate it from 0 to 2. And remember, you don't need to worry about the plus c, because you would have plus c for the upper limit and then minus c for the lower limit, and they cancel out. So when you have no lower and upper limit, it's a definite integral. You don't need to worry about the plus c. Alright, so what this means is you're going to put 2 in and get 8, and then you're going to put 0 in and get 0. And so the area under this curve is 8 units squared. Alright, now we are leaving the picture, and we're just going to solve this definite integral. So it's a definite integral because we have a lower and upper limit, and we want to take the antiderivative. So that would be 1/2 x to the 4th divided by 4 minus 3x squared divided by 2 plus 2x. And we want to evaluate it from 2 to 4. So we put the 4 in. That's going to be 1/2 times 4 to the 4th over 4 minus 3 times 4 squared over 4, over 2, plus 2 times 4, minus parentheses, now we're going to put 2 in, so that's 1/2 times 2 to the 4th over 4, minus 3 times 2 squared over 2 plus 2 times 2. And all of that is in parentheses. And then we're going to use our calculator here. So would be 0.5 times 4 to the 4th divided by 4 minus 3 times 16 divided by 2 plus 8. So we get 16 minus parentheses. And right here we're going to have 0.5 times 2 to the 4th divided by 4 minus 3 times 4 divided by 2 plus 4, and get 0. And so the area under this curve is 16 units squared. Alright, and the last one, we're going to take the antiderivative. That's 6x plus 2x squared over 2 minus x to the 4th over 4. And we're going to evaluate it from 2 to 4. So that means we're going to put 4 in here. 6 times 4 is 24. 4 in here. That's 16 times 2. These 2's cancel, so that's 16. And then 4 in here, need a little help on that. 4 caret 4 is 256 divided by 4. That's 64, so minus 64. That's your upper limit. Minus, now we're going to put 2 in, that's 12, plus 4, minus 2 to the 4th is 16 over 4, that's 4. Okay, so 24 plus 16 minus 64, negative 24, minus 16 minus 4 is 12, and you get negative 36. Okay, the last thing we want to do is prove that the answer that we got in B, negative 36, is correct. And so we are trying to evaluate the function from 2 to 4. I'm going to use 500 rectangles, use my dx formula. X is a2 or 2, and then I'm going to add dx to that. The function, now when you're doing Riemann sums, you do not want to do the antiderivative. You type the function in. And I'm I'm going to find the area, which is the height using the function times the width using dx, and drag it down. Total area was H2 to H501, and we got a negative 35.896. And we got the exact area of negative 36. So what I did is I graphed the function, which is 6 plus 2x minus x cubed, from 2 to 4, and you can see that it's below the x-axis. So what's happening is you got a negative area because it's below the x-axis. So we know that area can't be negative. So what's happening is you just take the absolute value of that area to figure out the actual amount that is underneath this x-axis. Okay, and everything that we do will be above the x-axis because everything we do is a word problem. So that's good news.